Okay, folks, I want to talk about building mountains. Really important part. Remember how we've spoken about how difficult it was to make continental crust, and we had to have some subduction to make that happen, to make some granitic rocks, that we could have something that was buoyant enough to not get subducted. Once we did that, what we had to do is we had to thicken the crust. Like, how do we make really thick continental crust? It's not an easy job, but I want to talk about how we build mountains and why they're so important. So the idea is a mountain belt. Here's a beautiful picture from Mont Blanc up in the European Alps, and you'll notice some amazing features there that glaciers are forming, and notice how there's a lot of snow up there. Great place to go skiing. So typically it's a elongate linear belt of continental crust with high elevations, really thick crust, 40 to 80, even 100 maybe kilometer thick crust, intense internal deformation. That's an important thing. To take regular crust and make it this thick, we're going to have to keep squashing it to thicken it. And so that's one of the common themes here. So we've looked at deforming rocks. Now we want to look at what that deformation of rocks does to help us make mountain belts. So down the bottom there is a neat thing. Ancient erodive mountain belts, commonly called orogens, and the process of formation is called orogenesis. This is from the Greek oros, and genos, meaning to make. So it's to make mountains. Orogenesis or orogeny. So we use these words quite often in various different ways, but orogenic is of or related to mountain belts. So anything saying orogeny, orogenic, orogenesis, any of those words means mountain, forming mountains. And we use them a lot. So if we look here, of course there's some amazing things, right? Like this series of rocks through here. And we've talked a bit about how you can see how India was down here with Gondwana and did a runner and went whack up into Eurasia. And there's the beautiful Himalayan and the Alpine mountain belt there. And then of course the longest mountain belt on earth, the Cordillera, starts here at the southern tip and goes all the way out here to Alaska. It's quite extraordinary. These we call the Andes, these we call the Rockies or the Sierra Nevadas. So these amazing mountain belts are something we're talking about today. There's other things to talk about. We used to have a pretty serious mountain belt here, but it's no longer active. So the reason mountain belts can stay really high is if they're actively uplifting, because then they can overcome the removal of material through weathering. If you stop uplifting, then you allow weathering to completely erode off the mountains. So you can get a feeling for once upon a time we had some active, beautiful mountain belts here, but now they've been sort of worn to a nub. We have some amazing orogeny happening on the South Island of New Zealand, which is actively moving up at a very fast rate. And there's a number of other things I might just point out here, since we're here and you're listening. One is that when we rift continents, we can see evidence of that, like the starting of making a basin. This is the East African rift. We're starting to crack it open and get a rift here, and with time these will spread apart, and this will be another new ocean. We used to have all of this material you can see in here used to be part of Eastern Australia, and we rifted it off and it moved out to sea. So this basin is a relatively recent thing, pretty much like we talked about this opened up when we broke Gondwana up, and Antarctica left 100 million years ago, and that's what we've built in the 100 million years. Poor old Tassie moved just a little bit and stopped, but a bunch of bits and pieces of Norfolk Island, a little bit of Tassie, a little bit of a whole bunch of these islands and rifts and pieces in here, they used to be part of us. And you can notice how as we move northward into poor old PNG and Indonesia, you can see how this Arafura Sea never gets terribly deep. It's just all part of the same piece of material, only we're subducting underneath there. So there's so many things we can talk about. You can see, for instance, the Hawaiian track here. We can see a neat hotspot track there. We can see a lot of things on here, a lot of transform faults across these mid-ocean ridges. So there's the Mid-Atlantic Ridge, there's the Mid-Pacific Ridge. And you can see how this Mid-Pacific Ridge has been subducted underneath western North America, making it quite active. Here is a volcanic arc, quite beautiful, isn't it? Right? Volcanic arc, volcanic arc, volcanic arc. So I'm hoping that this is all bringing it together in such a way that you're getting a good feeling for how the Earth works. So Mount Everest, of course, you all know, it's the highest peak on Earth. And you can see how the Himalayas sit way high above the plains to the south. Amazing shot from NASA, from outer space. So major mountain belts or orogens are produced by intense deformation of continental crust, usually adjacent to convergent plate margin. You guys know that. We've talked about that. And obviously we need a huge compression to get all of this stuff to uplift. So it takes a lot of work. Deformation involves large horizontal shortening and vertical thickening of continental crust. Major deformation processes include folding and faulting, which we looked at in the deformation snippet. Fault slip events generate earthquake activity. So mountain building and earthquakes are one and the same thing. Okay, so collision zone between the oceanic crust of the Nazca Plate and the continental crust of the Southern American Plate is making the Andes. And the Andes are an unusual mountain belt because it's sitting right there above the subduction zone where we get arc magmas. So this is the volcanic arc and the active mountain building. And that's an interesting thing we'll come back to. But the North American Cordillera is also interesting because we've got this plate coming down here, and we have a bunch of volcanic arcs along here as well. But not all oceanic continental convergent boundaries produce mountain belts, right? We've looked and talked about the Indonesian archipelago, a series of arc volcanoes, but they've never gotten very high, for the most part, or they haven't made a mountain belt. There are parts of, let's say, in Papua, where they're up to 4,000 meters. That's pretty high, 4,500 meters. But that ain't 8,000 meters, right? So it is high enough to have a glacier, but it's not a proper mountain belt. Okay, so we've talked about this before, about how when we take oceanic crust and we subduct it and we dehydrate the slab and we get a material ascending up to make a volcanic arc. That's part of the story. So mountain belts are produced only if the compressional forces due to plate collision exceed the strength of the continental lithosphere. In other words, they start to smash together enough to actually deform the crust. So mountain building and plate collision zones, crustal shortening, rates up to several centimeters per year. Okay, well, we talked about spreading as that, but crustal shortening means we are squashing the crust enough in that same sort of manner, pretty much equal to the spreading. Crustal thickening rates up to several millimeters per year. That's an important thing, is to thicken the crust is hard work. To uplift crust is hard work. When we talk about spreading rates, we talk about 3 centimeters per year. When we talk about uplift rates, we talk about the fastest being 5, 6, 7 millimeters per year. And we're now being able to measure that with fancy gadgets in space, telling us sort of micron movement. And it turns out that the South Island of New Zealand is moving upward at the fastest rate on Earth, something like 6 or 7 millimeters per year. Okay, so competition between crustal thickening and erosion is the battle here. If we have too much erosion, we will counteract whatever we're building up. So surface uplift, erosion, exhumation of rock from deep in the crust. Exhuming means exposing. So if you imagine a granite forming at some 3, 4, 5 kilometers depth, like up in the Snowy Mountains, and then we erode, eventually we will start to see granite peeking out, and it will be exhumed. So then at the bottom here, seismicity is associated with crustal deformation. Okay, now, I lost my pointer again. I'm going to pause for a second. Okay, I have my pointer back. Thank you very much. Okay, so here's a neat way to look at it. So let's just start with some thin continental crust, and we'll put a dot in the middle of it, just so we can track it. So here we are at point A here, and we have this nice little red dot in the middle. Now we're going to start to shorten and thicken. And remember that shortening and thickening are two of the same thing. If we're going to squash it together, it's going to have to get thicker. So the surface is going to uplift, as well as the stuff on the bottom is going to go down, right? Then we can erode some off, because remember, we're always eroding, and the mountains tend to take all the action. We'll talk about that later, how mountain belts attract the weather. So we erode back down, and now the dot has moved kind of up. So now we're going to see isostatic rebound due to the uplift. And that's a really neat thing. Isostasy means that stuff that's floating will actually bounce back if we push it down. So we essentially pushed it down by thickening it, eroding the top. Now buoyancy will bring it back up. So now we're going to raise it up a little bit. And after we do this a long time, we find out that the deeper stuff is now higher up. So erosion and isostatic rebound in response to crustal shortening and thickening is reduction of topography, exhumation of deep crustal rocks. This is how we get things from deep, get them up so we can have a look at them. So displacement of faults during plate collision, initial burial of rock mass. So if we think about when we had the Indian plate and it comes smashing into the Eurasian plate, we found that we were having thrust faults back up on top because we're trying to smash India into it, and with time we just keep smashing and smashing, and we're exhuming the deeper rocks to make the Himalayas. So that's a process by, we can say that we're smashing these rocks of the Indian plate, trying to push it under the Eurasian plate, and what's happening is it's being pushed back up this way. And notice how we have a reference point sitting here in the Indian plate. That in turn gets pushed up and it finds itself in the mountain belt. So the Himalayas are mostly made of the Indian plate because it failed to push itself under the Eurasian plate, and we smashed all the stuff up on top of it. So if we look at seismicity of the Himalaya, notice how much there is. So this records contemporary brittle deformation due to plate collision. And let me talk a little bit about that. When we get to high pressure and high temperatures in the mantle, we're not talking about brittle deformation, we're talking about ductile deformation. That's what we're talking about viscosity. Ductile means it can flow. When we get to a point where we're not viscous and we're solidified, we become brittle. And brittle deformation means things break and crack, and that's how we make earthquakes. Notice all the earthquakes there. Okay, so let's look at a few folds, right? I've talked about folds. You can see how we have some of these layers bedding down here, which is pretty happy, and then look at this. Wow, right? So that's where we're really starting to get folding. And these folds are where we have severe compression, where we started with happy little folds and we pushed them until they flopped over. So this is a fold lying on its side. And this is what happens when we push it and push it and push it, and eventually we have thrust faulting. And thrust faulting is a beautiful way to chuck rocks up on top of other rocks. So this is what they call a nap, N-A-P-P-E. Not a nappy, that's for baby shit. This is a nap. So here's a cool picture in the Canadian Rockies where we are crustal shortening and thickening by over-thrusting this material on top of that material. So we have low angle faults where we can chuck stuff on top of others. And what's amazing about thrust faults is we put older rocks on top of younger rocks. And we see this all over the world in orogenic zones. If we look at Australia, we have no currently active mountain belts. Our continent has been built up by many orogens, ranging in age from 3,500 million years to 200. So out here in the Yilgarn, this would have had some amazing mountain belts in the past, as well as the Pilbara, right? And then we have the Gawler Craton. These are some of the oldest rocks on Earth. Then we have the East Coast, where this is the Lachlan Fold Belt, and you can see how there's a bit of a mountain belt here from collision in the Paleozoic. And then we have the New England orogen here that had a little bit. So we have a series of rocks, some in central Australia, that record some really old mountain belts that aren't active anymore. So contemporary mountain building in our region, we talked about this, how we're actively making mountains in poor old New Zealand. And I asked you about why New Zealand gets all the crap. Why is it such a poor place? I mean, beautiful place, much more beautiful than most, but it's taking the Pacific Plate moving east into it. We're moving north, so it's being wrenched in a very strange way. As well as to the north of us, we're actively building some mountain belts through arc magmatism. Seismicity in our region, notice how all the earthquakes are somewhere else. We have some pissy little ones, but they are unimportant. So New Zealand is a convergent margin between the Pacific Plate and the Indo-Australian. We know that. Continent-continent collision in the Southern Alps is a groovy thing. And notice how we have this beautiful giant fault that comes right by the capital Wellington and right smack the Alpine Fault right through the South Island. That's why we have such amazing action there. And we have a bit of a plateau to the east here, but we've talked before about this. The Taupo volcanic zone is some of the most highest heat flow on Earth, and that is because we've got subduction of this material here underneath it. So I'm just going to pause for a second, which I believe is F1. Hey.
STB Labs are booked this afternoon. We can't use them for filming, so we need to bring everything up here to film.
Okay.
Luigi's going to meet us at 1, but I'll need your help moving everything.
Okay.
So when you're done that video, if you could...
Okay, we'll just bring it over here.
Yeah. Have you got your car here?
I do.
Sweet. That makes things much easier.
Yes.
It'll be a full carload.
Good, good. Well, I'm glad because this is our last chance.
Yeah.
They're going to close it.
Yeah. It needs to get done this afternoon.
I know.
Yeah.
And then we can do everything from home.
Yes. So, yeah, whenever you're done.
Have they announced it yet?
No, but the fact that another course has swooped in and stolen the spot this afternoon.
Yes, I only know because Matt Balatich's wife Lou works in Central. So he called me this morning. He said they're going to close it. They're piking. He thinks it's really wussy.
But like,
I think
us not being here, does that actually stop? I don't know, because they've already closed it to like just the Central.
I mean, they could have done. Yeah, I don't know.
And surely give us a little bit more notice than.
I know. And guess what? Brad will be completely unable to do his course. What are we going to do about it?
I mean, so you can do Zoom lectures, I suppose.
Yeah, but they won't make any sense.
No, they won't make any sense.
See, like I'm doing little 8 to 10 minute jobbies.
Which is good.
They'll love it.
Yeah.
I just want to get these online so they can watch them.
Absolutely.
Because they're going to have time to do stuff.
Yeah, we can put a lot of stuff online.
Yeah, yeah.
Anyway, I'll let you get back to it so we can get to that.
I'll come and tell you when I'm done with these. Okay, so that's the story there. We know that we have subduction occurring along here, and arc magmas here in the North Island, and then here we have some of the most amazing wrench faults and extreme uplift there along the Alpine Fault. So this tells us a few things. A, why they have such beautiful mountains. B, why they have so much amazing geothermal energy up here in the central volcanic region here. And notice here is a dot. Those are arc magmas because subduction along this trench is dehydration underneath there, and we could see how here's all the beautiful volcanoes and the geothermal fields sitting here due to extension ripping this open and arc magmas supplying massive amounts of heat. So they have active volcanoes, active geothermal, and active mountain building in New Zealand. If we look at seismicity, you can see that it's everywhere that this action is happening. Cutting through here, right, and up along the subduction zone. It tracks the subduction zone for us. There's a really beautiful picture of showing the Pacific plate and the plate boundary right smack there. And it's only been about 6 million years so far that's been doing this. So neotectonics of Australia began 6 million years ago, and that's another topic for another day. So here we go, Mount Cook, beautiful mountain, right? Actively uplifting 6 millimeters per year. So here's a beautiful picture of it, where we have the Pacific continental crust coming along here at 35 millimeters per year and coming up on top of ours, and that's making the Alpine Fault here and making the Southern Alps. Really quite simple. And here's a beautiful picture showing, some of the faults that you can track, and a beautiful mountain belt sitting right next to a plain that's completely unaltered, uninjured. So the main points: mountain belts or orogens are produced usually by intense deformation of continental crust near convergent plate margins. Deformation involves large horizontal shortening and vertical thickening of continental crust. Major deformation processes are folding and faulting. Australia built from mini orogens over a long period of time, from God knows 4 billion years ago to relatively recent 200 million years ago, when we became a passive margin. Present-day mountain building on the northern and eastern sides of the Indo-Australian plate, seismicity is expression of deformation in the collision zone. So collision zones include volcanism, which means when they extrude; intrusion, which is really probably more important, where they get trapped in the volcanic arc below the surface and become intrusive granitic rocks. Remember, those are buoyant. They help keep things floating. Accretion, we talked about accretion, where we chuck stuff onto land. So in all cases, we're seeing an accretionary wedge here, and we're seeing pieces of material that was once on the oceanic crust getting chucked on, abducted onto continental crust. This is a great way to build continents. So we build continents by chucking stuff, abduction of material onto the crust, and by arc magmas adding andesitic compositions, granitic compositions, to the continental crust to keep them buoyant. We also thicken them by folding and by faulting. So this is a nice picture to sort of reminisce about a lot of things we've talked in this course. Any of these pictures would be really fair game for me to say, oh, okay, there are old island arcs that have now gone dormant, and we're going to chuck them up atop the crust. Thank you very much.